Hello, I'm Vincent Roykers, and this is Lab 2. In this lab, we took what we did in Lab 1 a step further by comparing and contrasting the point model from Lab 1 to a equal distribution charge model in this lab. There are a few main principles we used in this lab. Again, we're seeing Coulomb's law and Newton's second law again, so I will not explain those repeatedly. But in this case, we had more of a focus on electrical field superposition. And this is the whole reason why we're using a computer model, or at least that is the main focus of this lab, because individually calculating the electrical field at each point along the model of the tape in this lab would be very tedious, because we have to carefully analyze each point charge of the total piece of tape and its interaction with the other point charges on the other pieces of tape. And then this is also why it's necessary to construct a computational model for this, as we need to find the vector sum at each of these points for each of the points. For observations, these are just repeated from the first lab, but for this I'd like to focus on the length of tape A, because I'm assuming both tapes to have a length of 10 centimeters for the sake of this lab, and I'm also assuming the same distance. I'll also be using the charge that I used or I calculated in the first lab. Because of my computational model, I am under the assumption that the new charge for the line model will be the pre-existing charge times an unknown constant. I'm doing this because I know the new charge will be in like the realm of what this charge is in terms of magnitude. So I'll be just guessing and checking to find that constant. Okay, so let's go look at our computational model. Okay, so here's our computational model. First thing to look at is here's our charge that we've determined that works. I knew the charge had to be larger than what it was in the previous lab because now it's more spread out, so it needs a larger overall charge to achieve the same electrical force. So I just started guessing and checking between 1 and 2 until I eventually found something that worked, so that's how I reached this constant here. So scrolling down again, here's our electrical field function. This is just repeated from lab 0, so it's essentially just the constant times the charge of the particle over the distance to the observed location squared, then times this directional vector. That's just what we're used to. And then going down, since the tape was 10 centimeters, I used a axis vector of 1 over 100, and then n is equal to 11. So this is what effectively gets us the correct amount of line charges for the sake of this lab. Then going to our E scale, I decided to use. I wanted to be able to see the arrow and the point charges, so I used the size of the point charges to determine how large the arrows should be. So again, we see that again for the force scale, the gravitational force scale here. Going down to the calculations. I guess the first thing it asks you to fix is to, I guess, calculate the overall electrical force. Again, we know that it's going to be again, the piece of the electrical field of the piece times the charge of the piece that wasn't already part of the electrical field, and that gives you the overall electrical force. And then we just add this together to get the total electrical force for that's acting on the top tape. And then we had to create a arrow. Again, this is just using the scale that I've previously determined, and I'm just multiplying this by the direction of the electrical field. And this is what gives us the arrows for each of the electrical fields at each of the different point charges, or like the net electrical field at each of the point charges. So we are then asked to create more arrows, and again, this just follows my previous logic for the scaling. And for the gravitational force, I know the direction has to be down, so I just multiplied it by the -1 y vector, and then we can just watch the program run. And here we see the magnitudes are equal, and they are going in opposite directions, and that the arrows look like they are correct because they're going away from the positive point charges. So now let's go into our conclusions. So here's the magnitude of charge that we calculated for one of the pieces of tape. There were two main assumptions made in this calculation, one being that there was no air resistance, and the other being that the charges were uniformly distributed throughout the tapes and that both tapes had the same charge. For the what if the why questions we were asked to answer, The main part, or the meat of the question, was that what was the difference between the charges that we calculated in both of the models. In the case of the point charge model, all the charge was concentrated in the center of the tape, and this location was the least distance between the two tape. This is why that charge was less than the charge that we calculated for the line model, because the line model, that charge is broken down into smaller pieces, and the different pieces at different points are further away. So we need a greater charge to achieve the same effect of the electrical force to counteract the gravitational force than what was needed in the point charge model. And it's also because of this that the line charge model is more accurate, because in the case of the tape, it wouldn't make much sense to have all the different, or I guess all the charges at the center of the tape. It would make more sense for the tape to have the charges evenly, or slightly more evenly distributed throughout the tape. And this is also, again, why that model the line charge model is more accurate than the point charge model. Thanks for watching.